Last class we had done on adiabatic flame temperature. The method is we assume two temperature. Okay, we assume two temperature. Then from the assumed temperature, we find out what is the adiabatic temperature by doing the extrapolation or interpolation. Okay, so what we did last time. Huh? Okay, so last class I had informed you there are another method that to determine the speed adiabatic apart from assuming two temperatures. Okay, this is the method where it calculates on the total of enthalpy produced by the gases. But at the end, they still assume two temperatures. Okay, so I will explain to you step by step. This example is from textbook. Okay, in textbook, thermodynamic by Chang'e, chapter 15, that one covered our topic, fuel and combustion. Your thermodynamic use what textbook last time? Is it Chang'e or Smith? Don't remember. You find out thermodynamics textbook by Chang'e, and then chapter 15. That one cover our course, our syllabus. Okay. So this one calculating adiabatic flame temperature. Same example as previous. Okay, same example as previous where it used liquid octane. Enter at 1 atm and 25 degrees C. Okay, it asks you to determine the adiabatic flame temperature. Okay, we focus on A only because I want to explain the method, the alternative method. The rest you can try to do. Okay, for A, when 100% theoretical air, that means X twice. Okay, as always, first step to generate the combustion equation, where you come out with this mole of product gases. We know that adiabatic flame temperature, H product equals to H reactant because Q equals to 0. Okay, that's why H product equals to reactant. Okay, product, reactant. So the reactant is equivalent to only liquid octane. Okay, reactant over here because O and N, there is no sensible heat and heat of formation is equals to 0. So that's why here it would equal to only liquid octane. Okay, here HF equals to 0. This one also HF equals to 0. So left only with the liquid octane. Okay. Then it arrange the infos in the table as we did. The heat of formation, the heat at reference for all the components. Okay, now after that, using the data that you extracted from the table, substitute all the data into the equation. Where total mole of product, okay, heat of formation plus sensible heat. This one is for CO2 product. So CO2, 8 mole of CO2 multiplied by HF and the sensible heat. Okay, sensible heat over here. In previous method, we assume the temperature. At initial state, we already assume two temperatures. Okay, in this method, it doesn't assume any temperature yet. This is the H at T adiabatic. H at T adiabatic, which is left unknown. Okay, because T adiabatic, we do not know what is the amount, the value yet. So this one is left unknown. This one is enthalpy at reference. Okay, this one. H prime, enthalpy at reference. Okay. So substitute for all infos. This one is for H2O. So the enthalpy at T adiabatic for H2O is left unknown. Okay. N2 enthalpy at adiabatic temperature is left unknown as well. Okay. Equals to liquid propane, HF. Okay, this one is the reactant. This is the reactant part. Okay, up to here, again I repeat, using this alternative method, instead of assuming the T adiabatic in initial state, they left the enthalpy at T adiabatic as unknown. Okay, they do not assume any temperature yet, just left the enthalpy for the component at T adiabatic as unknown. So here we have HCO2, H2O, HN2. Okay, unknown. Then this side you will have a value. For the reactant side, you will have a value. Okay, so rearrange everything, left the unknown to this left side. Okay, we have CO2, H2O, and N2, the unknowns. Then this one from the calculation, the earlier part. So this unknown equals to this figure. At T adiabatic, you must get this figure for all this summation. Enthalpy for CO2, H2O, and N2. Okay, at T adiabatic. Okay, how to choose the T adiabatic? In this explanation down here, all of this occurs at T adiabatic. So the H is equivalent to H at T adiabatic. Now this one you will still need to try and error. You will need to do try and error. So first guess is obtained by dividing the right hand side of the equation by the total number of the moles. Total number of moles over here is 8 plus 9 plus 47. Okay, so this side divide by this part. Okay, then you will get this figure. Now, these enthalpy values correspond to at this temperature for N2, at this temperature for H2O, and at this temperature for CO2. Okay, how to know? How to know? They refer in the table for each of these components. Let's say for N2. Okay, let me put the table side by side. Okay, we find for N2, table for N2 with enthalpy 88,220 kilojoule. Okay, we find for N2. Example H2O lah, H2O appear first. Okay, for H2O here it stayed at 2100 Kelvin. Refers to this enthalpy. Okay, at 2100. Here, around this figure. Okay, in this method, you find, instead of you find the T adiabatic in the initial state, you assume, in this alternative method, you find this enthalpy in each of the table for the components. This one, let's say for H2O, so you find this figure in the table for H2O falls under what temperature? Okay, in this case, it is around this, in between 2100 and 2150. Okay, so they peak at this temperature that appear closer to this enthalpy. Okay, then for CO2, we find at CO2, table CO2, we find that specific amount of enthalpy, so it falls under this, around this figure, 1800. Okay, so from here, we can see that enthalpy amounting 88,000 is different temperature for each component. For N2, you will find around at this temperature. Okay, so the statement over here, noting that the majority of the mole, noting that the majority of the moles are N2, we see that T product should be close to 2650. So this one, they are taking the temperature from N2 as reference. So the T adiabatic must be closer to this temperature. Okay, so they guess the solution here, it guess, still assume 2400 Kelvin, and another one is between 2350. Okay, here it guess, the first guess 2400. So plug in the infos at 2400 into the unknown equation over here. Okay, that means 8 multiplied by the enthalpy for CO2 at 2400. Then you plus enthalpy for H2O at 2400. Okay, so find the enthalpy at that specific temperature, equal them out, where this is the total enthalpy at 2400, where this total is slightly higher from the original total of enthalpy. Okay, so higher, so the second guess, the temperature should be lower from this. So that's why it guessed the second temperature, 2350. So plug in all the infos, the enthalpy for each component at 2350. Then you will get this figure, which is slightly lower from the original enthalpy. So from here, you still need to do the interpolation. Then you will get the T adiabatic is around this figure. Okay, basically, they still need to assume 2 temperature. But in this method, it calculates the total enthalpy for the unknown first. Okay, it's slightly more step compared to the previous that we apply. Okay, so in exam, you can choose either to use this method or straight away assume 2 temperature. Okay, both are accepted. Yeah. So I just want to share with you the alternative method, because if you read through the example in the textbook, it will show this kind of method. Any question? Okay, last time we had done with constant temperature. From previous example, it was constant temperature. Constant pressure. Okay, constant pressure. So we just use the first law analysis equation to find the T adiabatic. Okay, but how if you have constant volume? Constant volume system. Okay, constant volume. So the equation is slightly different, where it involves from first law thermodynamics. Okay, we know that Q is equivalent to U product minus U reactant. What is U over here? What does it mean by the U? H is enthalpy, U internal energy. Okay, thermodynamic, U is internal energy. Then from there, the H is equivalent to this, U plus PV. Okay, so from U equivalent to H minus PV. Okay, now we have the H, we know the H. We can get from the table. PV over here, it refers back to your PV and RT equation, the ideal gas. Okay, U product minus U reactant. Sorry, this is U reactant, U product. Okay, reactant initial equals to product final. Constant volume, so that means the volume here is the same. So it simplified the equation where you will have H reactant minus H product minus one value of the volume, then P initial minus P final. Okay, this one, the V over there, comes from the ideal gas law. We know that PV equals to nRT. Okay. So PV initial equals to PV final. Initial here refers to reactant. Final refers to product. Okay, rearrange from the previous equation. You will get this equation. Okay, so assuming T initial is 25 degrees C. This one is at 25 degrees C. So if let's say the question mentioned the T initial is at 7 degrees C. So you will need to find out the sensible heat of everything at 7 degrees C. Okay, so this equation is assuming at T initial 25 degrees C. So reactant minus product minus the RU, the gas constant, multiplied by this part. Okay, for constant volume, it will involve a lot more of calculation. So the T adiabatic, again, you will need to assume two temperatures. So by assuming two temperatures, you will have, after that, you will do the interpolation and extrapolation. Okay, so that means you need to calculate the Q. For example, you assume Q at T1. So you will have what is the value, then Q at T2. So what is the value? Using this constant volume equation. In constant pressure last time, simpler compared to this. The your Q is equals to N H product minus N H reactant. And then this H, we just refer to the heat of formation plus the sensible heat. Okay, this is constant pressure. But now for constant volume, it involves this part, the RU and the NT part. Okay, it involves this part. The first part is similar to constant pressure, this one. Now for constant volume, you will have this part. Similar step, assume two temperature, then find the Q at both temperature. Do the interpolation, then you will get the T adiabatic. Okay, any question before we move to the example? Now using this from this example, we try to do the constant volume. Okay, the question asks you to determine the constant volume, adiabatic flame temperature, T adiabatic with constant volume. For a start CH4 mixture, methane. Methane air. Initial conditions are this one, T initial 298, P initial 180 M. Okay, the heat of formation for methane is this. This one is from A26. This figure is from A26. Okay, let's say we assume the temperature to be 900 and 1500. Using this equation, you need to calculate what is the Q. Okay, here we already generate, first step, as always, generate the combustion reaction equation. Okay, make sure the A is correct, the mole is correct. If not, the rest will be wrong. Then find out the info at this particular temperature. Okay, always put in tables so that it is easier to see. Okay, find out the HF for the components. H at 900 Kelvin, H at 1500 Kelvin, and also H at 298. Okay, once you get the info, plug into this equation. RU over here is 8.314. Okay, you can use the RU 8.314, the gas constant. T initial is 298 over here. Okay, try to do it and let's see what you will get for Q at T900 and Q at T1500. That's all the things I see before. Okay, for Q at T900, you should be getting this figure 646051. Q at 1500, around this figure. Okay, then do the interpolation. Your T adiabatic should be around this figure 2991. Another method to find out the T adiabatic is using the CPBT equation. This one, again, you will need a few more infos to complete this CPBT calculation. I think last time this one you use in thermodynamics, right? Okay, so for those who are done, try to proceed with this. This question is from the textbook as well. Okay, you can pick a few questions in the textbook and try to do it. Those with answers. Okay, this one, it has a methane burned with 300% excess air in adiabatic constant volume. Okay, initial air and methane are at this condition. Now, assuming complete combustion, determine the final pressure and temperature of the combustion products. At this stage, you just assume complete combustion, because in the later topic, you will be introduced by incomplete combustion. Okay, that one a different calculation. So if the question doesn't mention whether complete or incomplete, you just assume complete. Okay. Now in this case, it already mentioned constant volume with 300% excess air. So first thing first, what you need to do? First step. Equation. Come up with the equation first. Okay. Methane is your fuel. Complete combustion, so you will have only CO2, H2O, excess air. So you have O2 and N2. Okay, excess air 300% excess air. So your theoretical air will be what? Theoretical. 100% theoretical air is 1. So 300 excess air. 3. So theoretical air. Theory. Equals to 3. Okay, so here 3. Here you have to find the A actual. So your A actual is the 3 multiplied by A stoic. A stoic. What is your A stoic over here? 2, correct. So A stoic is 2. Your A actual is 6. Now here is 6. So CO2, 1. H2O, 2. O2. This one you need to do the balance. Okay, for the B you need to do the balance. What is your O2 produced? N2 over here is 3.76 multiplied by 6. Okay, once you get the B, then proceed with assume 2 temperature. Assume T1 and T2. Then extract the data. Okay, list down in the table. Okay, once you extract all the data, then plug in into the equation. Okay, step 3. Input the data into the equation. Okay, this one, it already gives you the answer. T adiabatic is at 116 T Kelvin. How do you want to find the pressure over here? How to find this pressure? How to find this pressure? The T adiabatic you get from the interpolation or extrapolation. Then how to get the pressure? What do you think? David, what do you think? Where to get the pressure? Huh? From what? Huh? From the product fraction. Product fraction. Okay, T adiabatic is the product's temperature, which it involves properties for CO2, O2, N2, everything, right? This one, we can refer to the properties table. Okay, let's see whether we can get. Let's say we take for CO2 at 1160. Can we get the pressure? No, it's not listed. Which table that lists the pressure? It's not in the table. So what do you think? Where to get the pressure? Is it using the PV and RT? Okay. PV and RT. How about the volume? Constant volume. Assume. Can try. Okay, try first. Let's see how. Okay, for the P just now, for the constant volume, from this slide, this part is the one that equals to this one. Right, so here, this part is equals to V P initial minus P final. Okay, so once you get this part, you know the P initial, P final, then you can get the P final. Okay, so this part is equivalent to this. So from here, you can get the P final. P initial is 1 atm. 1 atm. So your final over here is in kPa. So convert this atm to kPa. Then you'll get your P final. Yeah. Let's try to do that. You can try to do on your own. Now for this example, to proceed for this example, where this example, it asks you to calculate the constant pressure, adiabatic flame temperature, okay, T adiabatic at constant pressure for A, and it asks you to repeat to find the T adiabatic at constant volume. Note that this fuel is solid fuel. A solid fuel, a gas fuel. So you are given this info where you have the ultimate analysis and proximate analysis. Now the ultimate analysis over here is in VAF. So to generate your combustion reaction, you must have the chemical formula of the fuel. For this question, you need to start from the beginning on finding the chemical formula. Right, where you need to do the correction. Here is VAF. So you find out the chemical formula, generate the combustion reaction. Then only you proceed with first step, combustion reaction. Then second step would be extract the data. Okay, this kind of question, it will bring a lot of marks because you will need to start from the beginning to find out the chemical formula. Okay, I would advise you to try to do this example in your own time. Okay, as of now, let's try to proceed with this first, finish up this one first. Okay, try to find out what is the pressure. Okay, let's just try to do this on this question and also the last example for this one, solid fuel. Okay, before we start, any question? No question, we can end the session and we are done with the adiabatic flame temperature. Make sure you are familiar with the steps, how to solve until you get the T adiabatic. Okay, next class, I will go for the combustion monitoring. Sorry, the water gas shift first. Okay. Okay, if no more further question, I will stop the session. Thank you.